Now we are going to move into the 3D elasticity, and this is a 3D problem. So you just think about 2D plane problem, but now it is extended into the 3-dimensional space. So the space is going to look like the following. And we talk about 3D space. We have the X, we have the Y, we have the Z, the Z, and elements of our interest could be pretty much like this. In fact, the structural elements for the 3D problem, these three mains are used. First, the 3D brick element. Number 2, tetrahedral. Hedral element. And number 3, the wedge element. We are going to focus on these brick elements as it is the standardized one. It is the type that you are used to with the construction of the basis function. The other elements are cheaper than brick element, of course. It has less nodes. The interpolation is not as good as the brick element. If you are talking about the same league, it is a brick. So you think of like the shape that I just draw actually. So you have in total 6 faces in order to constitute the brick element, and number of nodes in total at the corner, just the corner, you have 8 nodes at the corner, but you can have the higher order interpolation later on if you make the shape function to be something higher than the linear interpolation function. Next, tetrahedral. Tetrahedral, actually you learn in chemistry class this word tetrahedral. Tetrahedral, theta means 4, hedral sides, face, tetrahedral, 4 face elements. If you want to have the least number of sides in the 2D, you end up with a triangle in order to form a polygon. 3D is triangle is the smallest number of corners, smallest number of sides in order to constitute the polygon in 2D. If you want to come up with the volume in 3D, of which the number of, instead of side, it turns out to be the face. So with the least number of face in 3D, then you end up with the tetrahedral. You have 1 face, 2 face, the face here, and the face on the back. So in total you have 4 faces. Last one, wedge element. Wedge element just looks like wedge. So it is in between. Looks like the wedge. This is a wedge element. Yeah, it just looks like the wedge, so it is called wedge element. How many faces in total? You have 5 faces. Okay, so the number of faces is just different. But then we focus on the brick element, so there will be the mapping going on from the physical coordinates. Again, I think terminologies like this should be familiar to your ears at the end of the class. So physical coordinates or physical domain. So we need to map this into the numerical domain or computational domain because we do not want to conduct the integration with respect to the variables x, y, and z. We will have the node numbering like this. Okay, so node numbering is going on. The mesh generator, you're gonna end up with more headache in the 3D than the 2D. It is like exponential growth of mesh and of the algorithm in the mesh. If you compare to 2D matching tools, then 3D is gonna be much more. And don't mess up with the numbering, as I used to tell you. Don't mess up, because if you do, then the construction in the and I think I messed up. It was supposed to be switch around. Yeah. Because if you do, your point doesn't match correctly to the numerical coordinate. Shape function is set up that way, but you mess up. Oops, no. 1, 2, 3. Oh, you're supposed to be 4 here. 8, 6 was supposed to be here, and 4 here. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the mapping is going to happen from one to another. Yeah, mapping. Mapping here. We are going to see the following. Okay, yeah, let's map this way. So I have this one to this one. Oh no, not just this. Go up to here. I would strongly encourage you all to revisit the class notes as it is available on YouTube, so you can come back to see this anytime you want, not necessary to be during your time as a master student. You can come back when you work, at least to enrich your life a bit, because the knowledge is going to be updated. That's the part that I encourage you. That's the reason. That's the whole thing. I think there's gonna be a lot more to be like added into this course in the next year, so that will be good for you. I will think that it is interesting to know, to see something which is newer or not included in this year video. So it's gonna be more and more rich in the future. As time goes, I add more things, I put more content, and it should be more rich, and that's gonna be just good for you. If you still think that structural engineering is gonna make you money, but if you change to do some other things, then it might not be that useful. Okay. Now I will set up the coordinate. So the coordinate, the numerical coordinate will be at the center of this thing. Let me just figure out the center of this. I will erase it later. Center of this is in here. Okay, so the center move it up. How about other classes? Is it on time, which is supposed to finish very soon? I think this class we are good. I think we gonna need just a few more and we're gonna be done. So the line has to be well, we can erase all that out later. Nah. So the line is going to pass that thing. Yeah, no. One. Okay. Let me erase the scratch line. Where's the right line that I use? Okay, this one is deleted. This one is also deleted. No. Just need this one out. Okay. Here we go. I just make it longer, but resizing is not going to work because it's gonna make the line thicker. So okay, here we go. So we set up the numerical coordinates. Like so. Which one is going to be C? Which one is going to be eta? Let me figure out. We're gonna follow the right hand rule, of course. The point is that I set it up in the way like this, so the C was supposed to be going okay, so C is this one. One sec. Eta. Okay, like so. And if you have your eyes looking from this view, you'll find that you're gonna see the C and eta like this, right? If your eyes looking from the top, like a people in heaven looking back down to you, you see this, and you're gonna see 1, 2, 3, 4. So here is your 1, 2, 3, and 4, and 5, 6, 7, and 8. So the way the numbering goes is consistent with the 2D problem. We make it this way. if the coordinates on the back is confusing to you, let me just help you this way. Okay, looks better. And this thing and this there it is. Boop. That's it. Okay. Maybe it looks less confusing than before. Not too many axes. Okay. So the mapping is going on this way. Then let's see how the shape function is casted. At any point, we have first the physical coordinates. So you have x2, y2, and z2. And at a given point, well, for the x, the displacement along the x direction is going to be called u. For the y, it's going to be v. For z, it's going to be w. And then at a given point, you're going to have the u2, v2, and w2. Three things going on. All of these are going to be approximate. So the x subscript I, okay, the x only, is going to be approximated by summation of I from 1 to n. That depends on the shape function that you use and of what. So you're going to have the xi phi I. The phi is a shape function, so it is cast in the c, eta, and this thing. Well, I actually end up with the problem with this thing, the calling of this thing. So let me do a little googling up the Greek letters and how it's called exactly. I always be sloppy with this. So so this was supposed to be theta. Okay, theta. Okay, theta, and where is my yeah, C is properly called already. Okay, so this is theta. Okay, great. Come back. So C, eta, and theta. Then same for all. The same set of shape function was used for this approximation. Erase and we'll stuff in something in. So x, y, and z can be approximated by the nodal point coordinates x, I, y, I, z, I, like the u, like the v, like the w, that is going to be approximated by the nodal point displacement solution. So this is how the approximation is going on in the 3D, which is identical to 2D. The point is that how do we come up with the phi? So let's make the shape function. Shape function for 3D. Phi1 is equal to, same old tricks gonna be applied. In total right now we have 8. We're gonna have more if we deal with the higher order brick element. But for 8, I would like you to imagine first 8 nodes. At each node you can see that you have a bunch of degree of freedom. That's the 3 degree of freedom, right? 3 degree of freedom at each node. 1, 2, 3, 4, 5, 6, 7, 8. 3 degree of freedom each. That means for the brick element linear interpolation, you will anticipate how many? 8 multiplied by 3, that makes 24. Your stiffness matrix extend over 24 by 24 entries. That's a lot of fun. Okay. So we will start first at the node number 1. Node number 1, if we look at the coordinates, C, change the color to the orange. C equals to -1. Eta equals to -1. And theta equals to -1. So they are all -1. If they are all -1, okay. So we have the combination, the multiplication of these 3 in order to establish the linear interpolation in each axis. And if you stuff in 1 minus -1, 1 minus -1, and 1 minus -1, you end up with 8. You're gonna get the 1, 8 scaling out there. And likewise, okay, so let's see the second one. I will bring all of this to the side. So the second node, your C is equal to 1, others are -1. So C is equals to +1, then 1 plus C. Eta equals to -1, so that's gonna make 1 minus eta, 1 minus -1, right? And so on. So the only change is at the C. How about the next one? The next one, number 3, C is still equals to 1. Eta is equals to +1. But theta is -1, so plus, and like that. And the last one, C is equals to -1, eta is +1, and theta is -1. Next, when you talk about the upper layer here, 5, 6, 7, 8, theta are all equals to +1. So let me make it this way. And for the C, it's gonna be like before. So minus, plus, plus, minus. Eta is gonna be minus, minus, plus, plus, like this. That's it. Now, you're going to need to know the derivative of these shape functions, because you are going to deal with strain displacement relationships. Well, I'm going to come back to these derivatives in a bit after we talk about strain displacement relationships. First of all, I think I just want to remind you that the relationships that constitute the 3D elasticity is the relationships between stress, sigma in all three components, and tau xy, tau yz, and tau xz. So the component lambda plus 2g and lambda plus 2g and lambda, and we have 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 and 0 0 0. Shear 0 0. Epsilon x, epsilon y, epsilon z, gamma x, y, gamma but y z, and gamma x z. So epsilon x is partial derivative of u with respect to x, epsilon y partial v with y, and partial w with z. This is partial derivative of u with y plus partial derivative of v with x, partial derivative of v with z, plus partial derivative of w with y is partial derivative of u with z plus partial derivative of w with x. So our job is to find this, and these sets of partial derivatives is going to be given below. So this basically this is a strain vector, right? So from the strain vector, should I put the music as a background when I am silent? And okay, just do it this way, faster. So our goal is to write the strain in terms of one matrix, which is what we call the B matrix, the strain displacement relationship, and the displacement vector. And displacement vector is in here. We have u1, v1, and w1, u2, v2 there, and w2. So this pattern repeats, and now we'll see. Since first of all we have 3 repeating units, and that means the column we're gonna have in total 3 columns in one repeating unit, as the degree of freedom per one node is just 3. Okay, here. And first, partial derivative of u with respect to x. Partial derivative of u with respect to x, we pull out the u out there. So you have the partial derivative of shape function, which is phi1 with respect to x, and then 0, 0. Partial derivative of phi1 like before, but with y. Partial derivative with z, because the third column, this is u1, this is for v1, and this is for w1. So it goes like this. Now, what next? U with y, u with y, so phi1 with y. V with x, phi1 with x, nothing to do with z. V with z, so 0 here, and v with z, and w with y, and u with z, and w with x, right? That's it. Simple. And then repeat it. And then we will next look into the detail of each of this. No, too tight. Can it be another? It cannot. So forget about it. Delete. I will put the dimension of this. So this is what the 6 by 3 times element type, if we will stick with the element type variable. So if this is the 8th node, in total the size of this matrix strain displacement relationship is going to be 6 by 24. And no. And this one is going to be 3 times E type and by 1. Like this. And this is our B matrix. Strain displacement relationship and it is going to be like this. Okay. B matrix is established. What's inside the B matrix? The pane. Well, not the pane. It is durable for us. We have partial derivative of shape functions with respect to the physical coordinates. So in order to convert it, in order to find this, let me go through just one at a time. So partial phi with x is equals to, we're gonna use the chain rule like before. Partial phi with C, partial C with X plus partial Phi with eta with X and partial with theta and partial theta with X. Just that. Basically, you just have more work to do. That's just it. And in fact, paste. This is with Y, with Y, with Y, and with Z, with Z, and with Z. So, two major components. First, we need the derivative of shape function with respect to all local coordinates. So the first three will be from here. We take the derivative of shape function with respect to C first. And that is I think we're gonna need space. Okay, I prepare space and here it is. Take derivative of this. Okay, partial derivative of this term, right? You do not have anything from any contribution from the other part, so you have minus 1 over 8. 1 minus eta, 1 minus theta. Next, 1 over 8. Then it is easier to do it this way. No, not yet. We can just copy it like this. So we have everything there. Hey. Why didn't I just do it this way at the beginning? This is not smart. No hurry. Fine. We are ahead of schedule. So we can just take it easy. Go just as slowly as just as slowly as this. Oh boy, yeah. And that is this and for number 2, C is 1, eta is minus 1, theta minus 1 like before. Number 3, C is plus 1, eta is plus 1. Number 4, C is minus 1, so it has to be out there. And 5, 6, 7, 8 like this. So for the number 5, c is minus 1, eta is minus 1. Number 6, c is plus 1, eta is plus, no. C is plus 1, theta is still minus 1. Number 7, theta is plus 1, c is plus 1. And number 8, c is minus 1, and eta is plus 1. So we have the shape function for all of derivative with respect to c. A little laborious. Now, partial derivative of phi with respect to eta, it is going to be equal to 1/8 times with eta, then 1 minus c is going to be there, and 1 minus theta is going to be there, and we will not just miss like last time. It will be fast. And let's move this a bit. This is around this corner. Okay, there it is. And then copy and go ahead, paste it. Paste what? Just paste. Yes. And copy this and paste, and copy this and paste. Okay. Alright. For number 1, c is minus 1, eta is minus 1, so minus is there. Well, let's fix the alright. And c is minus 1, c is plus 1, c is plus 1, eta is now plus. Okay, so minus plus for eta. Sign for c is minus plus minus. This is all minus. Good. Next, where is it? Okay, I need to label the number 2, number 3, number 4, number 5. Number 5 again, minus, c is plus already, and c is plus, and minus 7 and 8. Okay. Beautiful. And the last thing is going to be for the eta derivative of shape function with respect to theta, not eta, sorry, is equal to 1/8 times 1 minus c and 1 minus eta. It is going to be an easy task. Put it here. Copy again. I forgot one thing, one silly thing. Here, since the theta is minus. First, okay, let's start like this. C is minus, plus, plus, minus. Eta is minus, minus, plus, plus, right? And then I'll be copying this, paste down there before I put the minus sign for these first four. Okay. And then we need the minus sign for all, because theta are all minus here. Minus, plus, plus, minus, 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 plus, plus, and then the below are following the same convention. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's it. Shape function is there, and the derivative of shape functions are out there as well. The next part is this is done. The implementation in the computer is just the next step for this part. Nothing more to do in the paper, but we are done with the red dotted circle. How about the green? So these greens are from of this here. Partial derivative of local coordinate with respect to the global one. This is page number 2. One, okay, like this, 2, like this, okay. So we can find all partial derivative of x with c. This is going to be equals to summation of xi partial derivative of phi with c, right? And then you sum it up. It could be called like a xi comma j. If I is 1, it means the x, I is 2, y means y, x, like x 1, 3 means the partial derivative of x with respect to, like this, or x 3, 2 is 3 is a z with the eta. You might find this index notation when you read the books in continuum mechanics or finite element. It is quite effective to write things down that way, so it is faster to expand all the things, but it doesn't really matter. I think it is just easy. It takes time, of course. Like this. I just expand it out and I can copy it, and it doesn't take time over here. Oh. last year notes is not as neat as this year, and not as detailed as this year. You can see 2019 April 18. So I didn't give you much information though. Okay, time integration. Okay, come back. And just finish the whole thing up. So we can change just x to y now. These are going to be in the 3D code. And Z, So basically, the operation is just simple. You are going to have the loop from 1 to n to e type, and then you loop over. You have the first x for the node 1, y for the node 1, z for the node 1 multiplied by this, which is going to be evaluated at the integration points. So the coordinates of the integration points going to be given, and the loops over integration points gonna work, and you're gonna get the partial derivative of this evaluated. Now the point is that you have all these evaluations, but it is the derivative of the global to the local. Now how to convert it to what you need the local with respect to global. So we work on pretty much the same thing like before. We have the setup, partial derivative with x, partial derivative with y, partial derivative with z. And that is equals to something with x. That means the chain rule is going to apply, right? So with x like this, and with y with z. So I'll be copying and paste. I'm thinking of how to make the homework for the plate problem. It's supposed to be set. I don't know what could be the fun thing to do in the plate bending if you have the code that I produce already. It is finished, and what else could you do? And this part here is multiplied with the partial of this with respect to C to eta and yes, to theta. Just that. And then pretty much the same thing. Applies. But this time it is just the reverse order of this. So you have the reverse of and this turns out to be x, y, and z. And you know, if it turns out to be x, y, and z, then up there it's got to be changed to x, y, and z first. And down here it's got to be the C for the entire row, and the other row is gonna work the same way. So C, and sorry, I should copy first so I don't have to delete later. Semester ends. Eta and theta. Okay, that's it. And now we be ending up with fact that this one here along with this one here, yeah. So this one and this one, they are identical, right? That means these two are the inverse of each other. Oh, I will take this paste. Which one is easy to find? This one, possible, easy to find. Things inside this matrix, well, you can go up there, right? X with C, Y with C, Z with C, eta, and so on. You can find all these and put in the matrix and inverse the matrix. So once you invert, well, you can let the software inverse that for you, or you want to inverse by yourself and give the value to the software to octave. That's up to you, but you will have to identify, fill in all the numbers into this 9 by 9, and then you inverse. That's the thing. Should we just give the closed form and then not let the software to do anything? Let me look up inverse 3 by 3 matrix. Well, and it is going to be long because you're gonna need the adjoin the okay, let the software does the job. Okay, software does the job, then you inverse the matrix. Now you are ready to put everything in here. You get all the entries ready to fill into the B matrix, and from this point your B matrix is ready. Then you come to the numerical integration. No. The matrix, stiffness matrix, is equals to integration over your physical domain of the B transpose D and the B dx dy dz, and then we use the numerical integration. Numerically integrated. And that makes it in the numerical coordinates Jacobian of transformation is gonna be there, which is the determinant of that matrix, and d c, d eta, and d theta, just like this. The whole point is that if you want to make the code for 3D or not, did you switch the screen? I didn't switch. Which screen? 2 minutes ago. I almost switched, but I didn't switch for the inversion, right? Okay. Here is it. Yeah, I think I can make it like a homework, but I can probably cast the framework of this 3D elasticity for you. I might not finish it up, the whole thing, because we still have time. Half an hour, I think we can do some Octave coding. Okay, so Octave is coming up. I'm changing the screen for you. I'm gonna make the new directory 3D. Should it be here? Okay. So I made the 3D directory and it is empty. And I'm gonna make a new M file. So DSHP derivative of shape function .m, like before. Function DSHP, increase the size for you. Element type, right? You need element type, you need the C, you need the eta. All of these gonna constitute the B matrix. But before it turns out to be the B matrix, it was supposed to be the D. We need the dn, dc. We need the dx, dc. Okay, that means we would have the x, y, temp, x, y for the element x, y coordinates. Okay, the more we go, we're gonna find more. Actually, it should be easy for you to just imagine what's gonna happen in here, because you have seen this for 2D elasticity already. Then this is just nothing new. It just has more things to do. So if E type is equal to, I'm gonna make 8, okay, 8 nodes. And now where we will need to use of this here. Okay, so the DNDC. Switch back. I'm going to cast the relationship for all of these in by coding it up. I don't understand my Apple Pencil 2. Someday it is very sensitive. Today I check it like crazy, it doesn't move. Okay, let's switch back. So the NDC has to be assigned zeros. We have 8, right? We have 8 shape functions, and we have derivative with respect to 3 local coordinates. And first of all, DNDC, the real DC, and you're gonna have the DND eta, and then you're gonna have the DND theta. Okay, and the DNDC is like this. Of course, there's gonna be 8 of these, so I paste and copy and paste and copy and paste. That's it. And it's gonna be 1, 2, 3, 4, 5, 6, 7, and 8. Before I copy everything here and paste in there and in here. And what else? One. 2, 3. Okay, that's all. Every single thing has that 1/8, so it is 0.125 multiplied by. Oh, so you don't have just C eta, né? You have theta. And you have one something with eta, one something with theta, and multiply by, make it 1 like this. I think it is easier to account for the sign. And yeah, that's pretty much it. I copy and paste. Coding is not difficult. Alright, and then you come back to this thing here. So start with minus 1/8 minus eta minus theta. Switch back to you here. Minus 1/8 is gonna be here, minus theta and minus eta. And then you can look at the next one. So you might have the notes. 1 minus eta, now it is a plus. Okay, so I don't do anything with this one. The third one, 1 plus eta and 1 minus eta. Eta is going to be always minus, and it's gonna be always plus here and here and here. Okay, and eta is minus, minus, plus, plus, and minus, minus, and plus, and plus. Okay. C is minus, plus, plus, minus, so it's gonna come like this: minus, plus, plus, and minus. Done with the first one. Next, come to the partial derivative with eta. So you're gonna need 0.125 again, multiplied by 1 and c. I should make a c. And what? Theta 1 something theta, and multiply by the sign. I switch you back here. First of all, I think this is going to be the nightmare. Eta is all in the lowercase, theta. That's it. So 0.125 something with c, something with eta, and then first line is the minus, minus, plus, plus, minus, minus, plus, plus. Okay, the sign's gonna look like this. For theta, 1 minus, 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 and plus, 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 and plus. And c, right? C is minus, and it is plus, and it is plus, and it is minus, and it is minus, and plus, and plus, and minus. That's it. Last one, 0.125 times you have something to do with c, and you have something to do with eta. For the theta, like this, it is a derivative. Copy and paste. And nature of c, minus, plus, plus, and minus, minus, plus, plus, and minus. Eta, minus, minus, plus, plus, minus, minus, plus, plus. And theta, all minus. Okay, here it is. Done with derivative of shape functions with respect to local coordinates. Now we will need the we get the NDC. We were gonna need the DXDC, right? Actually, what we send out, do we send out any DXDC? When we send out, we get derivative of shape function with respect to x, so the xdc is not used. We get the dc dx. Yeah, the xdc is not used. Actually, we can compute dc dx just right away. It is like an improved version of the previous code. but still we need to assign the xdc, and it can be assigned from the outside. The xdc, and we need to make some sort of note. Okay, the xdc 1 means there are 9. What? Why is it jumping back there? Three, 1, 2, 3, 1, 2, 3, 3, 3, 3, 2, 2, 2, and 2. So we will look back into the meaning, into what we have from the developments here. Partial derivative of x with x or y or z with the row number 1 x with c, row number 1 column 2 y c and z c. So switch back. This is dx dc, and then dy dc, and dz dc. We move over to the row number 2, dx d eta, dy d eta, and dz d eta, and then row number 3, dx d theta, dy d theta, and dz d theta. Okay, so we understand all of this. Well, that's because sometimes if we derive and we don't have this order, so dx dc is equal to 0, 3, 3. Okay, and it could be computed. The temporary element x, y, z. Okay, let's make it this way. Element x, y, z means element x, y, e, x, y, z. E, x, y, z means the element x, y, z coordinates. So the e, x, y, z is coming in as the input. Now I'll bring you back here. So we need to find this one, right? Partial of x with c, etc., etc. That means you're gonna need to do the summation, which is equals to element type, for this case 8. So we're gonna have for loop for 8 times, and for each of the for loop, this will be accumulated. Switch back. So I make a for loop here. For I equals to 1 to 8, because this is within the if, then we don't need to call the variables, we just say 8 explicitly. and the D, what is that name? DCDX, DXDC, huh? DXDC 11. We're gonna talk about all of them. So DXDC, comma, add up with, right, we just accumulate. So I'll bring you this one here. Just look at this one alone. Itself is this thing will be the accumulation of the nodal point x value. Okay, that will be from EXYZ, from EXYZ, and this is from DN DC vector. Come back here. Element XYZ. What will be I first? Of course, because we are talking the node number I. Well, whatever it could be X and Y and Z coordinates. We're gonna just drop into this index later. Multiply by DN DC and of what? Of I, right? I for the shape function number associated with the node, and then comma what? That depends, and that's it. Okay, you close it. And so the first thing we're gonna find the X, Y, and Z. Derivative of global to local C. Okay, we just need to see. And there are three, right? And you have the derivative with eta. And you have derivative with theta. Okay, and that's it. N4. So let's start. X with the XDC, and this has to be 1, 1, 1, 2, 2, 2, 3, 3, 3, and this is the accumulation 3, 3, 3, 2, 2, and 2, and 1, 1, and 1. And X, Y, Z. Okay, so node I, this is the X, this is the Y, this is the Z. X, Y, and Z. X, Y, and Z. Okay. The X. So this got to be 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. And this comma DNDC This got to be 1, 1, 1, right? It looks confusing, but I'll come back here. Come back here. The first row, it is coming from the partial derivative of phi I with respect to the C. So with respect to C, then that means D and DC I, comma 1. And then the second row, comma 2 stands for eta, and comma 3 stands for theta. Come back. So make it 2, 2, 2, and make it 3, 3, and 3. And this accumulates the values. We reset to 0 at the top there, and element x, y, z, element x, y, z, yes, 1, 2, 3 for the coordinate x, y, and z of that given node, multiplied by partial derivative with respect to c, partial derivative eta, and eta. Okay, looks good. So the next step is to perform this inversion, and then we are going to get c with x, eta with x, and theta with x, like that. Actually, if we can make a small window of iPad on the corner, and I will be able to talk about later. I will set up the screen like that, so maybe half and half, and you can see the operations. Well, it is almost the end of the course already. Too bad. Yeah, just figure out that it might help, but too late. Okay, so I think we're gonna need the explanation of this is called dc dx, right? And dc dx, I'm not going to change the screen now, but dc dx 1, 1, yeah, the corner here is the dc with respect to dx, and this one the eta, the eta dx. Okay, likewise, just come back here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. And the theta dx, the theta is going to be with y and going to be with z. The eta is going to be with y and z as well. And dc dx is going to be dc dy and dc dz. Why z here? It was supposed to be y. 1, Okay, we have a nice node already. Then let's get the dx is going to be dx dc inverse. But how do we inverse? Like this, right? Just inverse. And JCB as a Jacobian of transformation is computed from the determinant, but I don't remember determinant. Is it going to be just it? If A is equal to 1, 3, 4, 2, det A, is it working? Okay, yes. So I go for the det A equal to det dx dc. We have the determinant of this one as a Jacobian of transformation. So the Jacobian of transformation is something that as the output there, JCB. dn dc is going to be used outside, dc dx is going to be used outside, Jacobian of transformation is going to be used outside, right? And if and that's it, and save it. So I open a new function 3D main. I don't care what's inside. For the admin part, I will not work on it for now, but I'm gonna just give you the main part for I equals to 1 to NLE. First of all, you are going to obtain the element x, y, z. Okay, an element x, y, z has to be allocated with zeros. Number of row if element type, the number column is going to be 3. And element x, y, z has to be obtained. So for j equals to 1 to element type element x, y, z, we're gonna have 1, 2, 3, comma, this is equal to xy core. Xy, actually there is also the z, but I call xy core. Xy core, we try to make use of the same. Xy core is equal to nmap is going to be there again. Nmap of element I of the node j, comma, this. So the x, y, z coordinate is going to be transferred to that given row, and that will be obtained from the row of nmap ij, element I and the node number j of the element. So we talk about node 1 at a time. And n4. No, just don't understand me. And next step, once we get the xy core already, we are going to xy code is not going to change. We are going into the integration, numerical integration. So for again j equals to 1 to nint, not going to change this. What's inside? First of all, the c is equal to eta is equal to theta is equal to I remember that we use this one J1. We're gonna make the function dedicated for this integration point. Okay, we assign the integration point, we obtain the integration point. Now we are going to evaluate the shape functions and derivatives. Call it this way. Okay, so we're gonna get the ndc dc dx Jacobian of transformation out of this thing. And we are going to compute the B matrix, which is going to be zeros. How many rows? 6 rows. How many columns? 3 multiplied by element type columns. And then we get into the B matrix for whatsoever type of element. For k equals to 1 to E type. And we learned already that the B matrix has the nature of repeating cells, like three times the element type columns. So we're gonna do it column by cell by cell. So first cell, come back here, is going to be in here. Oops. This, and this. Okay. Come back. First is the B mat. It's not 1. It is 3 multiplied by k minus 1 plus 1 comma 1 equals to partial derivative with respect to c, okay, dn dc the first index stands for the node number, right? The shape function number. The second index stands for the dndc, stands for the c. So the first one is a c, and that means it's gotta be multiplied by d c dx, but dc dx, go back and see dc dx, dc dx, 1 is dc dx. We can copy this and put there as like a scratch paper. So dc dx, we need dc dx, so that's gonna be 1 plus of course K1 is not good anymore, right? It has to be 2, and we need with respect to x, so the first index is 1 and second index is 2. So eta is here, and paste, and theta is here. Okay, we're gonna do this quite many times because you have 1, 2, 3, 4, 5, 6, 7, 8, 9 points, 9 entries. So the matter of fact is that you are going to just work on this. We can come back and work on all of this later. I think make it your homework. Okay, next homework is this one, 3D problem. Okay, just save it. main. I'm not sure if I put the number 3 like that and it's gonna work, so I could do it T. I'll put this on the Google Drive. Your homework easy, just finish the I don't expect much. I just want you to finish this part. Okay, finish this part here from the beginning of this 4 to end of this 4. Do not change my index K, J, or the other things. Okay, do not. So finish this up. You have you turn in on Monday to Hang like before. In the morning, no later than no later than, not in the morning, no later than 6 p.m. Turn this in. It shouldn't take much time. Actually, you should finish it by today. But you will have some other classes. Tomorrow you can finish it up. Okay, let's keep it in the evening of Monday, 6 p.m. Okay, guys. I think I'm gonna finish up the class here. We will come back, and I think for 3D elasticity you do not have anything much more. Well, you have seen pretty much already, so you can finish up this code, and the thing is that, well, we might be able to finish up and to plot, to analyze something cool, but the thing is that the user interface, the matching, the other admin stuff, admin issue is gonna come involved, and when we develop the code, we need to pick up all those points. We cannot just pick up the developments, just selectively work on the development we had in this, right? Because it has more, it has much more than just what we see in this development. So it will be more like the admin issues, and it could be done, but I don't want to do, just waste time, and finally this code is not going to be used for real, but it is just for understanding what's going on in the 3D elasticity problem. So we might just leave off somewhere around here, or I will see if it should be continued in the next class. But we have some other interesting issues like the time integration, and the time integration can be done, and we can play with a little code for time integration in probably bar problem, or even in the 2D elasticity problem that we already established. It could also be done. So we'll see. The best case scenario is to do the how is it called, the wave propagation. That will be cool. Yeah, if we do the time integration into the elasticity, you might see the wave propagations. Right now we come this far to the visualization in figures, like but if we do the time history, then it's gonna be the video visualization. So you're gonna see the movement. You're gonna feel like you're smart, to be able to do all of this, whereas many others cannot. We are the user that understand to the roots of the FEM programming. So that's going to be useful for you in many aspects, like when you do the research. That could be useful to be able to play with a lot of things in MATLAB Octave and do sort of visualization like this. Anyway, I talk too much. I think I wrapped it up now, and I'll see you again on Monday. Probably we might just leave off the 3D and jump to the time integration, but the 3D homework is gonna be with you, and you need to submit it in. Okay, have a good weekend. I'm not gonna see you tomorrow. Bye bye.